Here we are again, looking at a redox reaction. With our alcohols, we looked at how the alcohol carbon can undergo oxidation by losing carbon-hydrogen bonds and gaining carbon-oxygen bonds. Here, we are looking at the reduction of a carbon, which means we're going to go in the opposite direction. We're going to see an increase in the number of carbon-hydrogen bonds and a decrease in the number of carbon-oxygen bonds. Reduction occurs because we are reducing a carbon, which means the carbon is gaining hydrogens. This process is also known as hydrogenation. So we are adding hydrogen onto the compound. We have seen this before when we were looking at our alkenes and alkynes, where they were undergoing hydrogenation, breaking the double and triple bond to form that saturated hydrocarbon. This is a very similar process. However, because we're starting with a carbonyl with that aldehyde, we're going to reform that primary alcohol. This is essentially the reverse of the oxidation of our primary alcohol, and now we're just going to go back to it. Like we had done with the oxidation of our alcohols, where we tracked our carbon-oxygen bonds and carbon-hydrogen bonds, we can do the same thing here as well. So in our aldehyde, we have 2 carbon-oxygen bonds and 1 carbon-hydrogen bond. Because this is a hydrogenation process, we're adding hydrogen. Hydrogen is the molecule we are using. What's going to happen is 1 hydrogen is going to be reattached to that reactive carbon, or the carbon that has the functional group, and the other hydrogen will go back to the oxygen because we have to break that double bond in order to add the hydrogens back on. Like we had seen with hydrogenation of our alkenes and alkynes, we needed to use a metal catalyst. The metal catalysts are the same here: nickel, platinum, or palladium. Like we had seen with our other hydrogenation, the nickel catalyst serves as a surface, orienting the molecules for bond breaking. The nickel catalyst facilitates the dissociation or breaking of the hydrogen gas into individual hydrogen atoms. And this is a required step in order for those hydrogens to be added to the carbonyl. So once those hydrogen atoms have been re-added, we can see that the number of carbon-oxygen bonds has decreased down to 1 because we reformed the alcohol by breaking that double bond. And we've increased the number of hydrogens from 1 to 2. That is that process of reduction, or the opposite of oxidation. Looking at a real aldehyde, here we have methanol, and reacting with our hydrogen in the presence of a metal catalyst, I put platinum here, we are going to be able to break that double bond. Like with our nickel catalyst, so assume this tabletop is that nickel catalyst. That nickel catalyst allows for the breaking of those hydrogen bonds. So now they're available to react. Because we have this double bond here, these hydrogens are now in a reactive state to break this double bond. It's going to break open that double bond, allowing 1 hydrogen to be added to that reactive carbon, and the other hydrogen to go back onto that oxygen, reforming our primary alcohol. And we can collapse this down into methanol, which is CH3. When we were looking at the oxidation of our alcohols, we had to know the classification because the classification of the alcohol dictated what the next functional group or product would be. A primary alcohol made an aldehyde. A secondary alcohol made a ketone. Aldehydes and ketones are both carbonyls. Therefore, when an alcohol undergoes oxidation, that hydroxyl functional group changes into the carbonyl functional group. Therefore, in the reverse process of reduction, our carbonyl functional groups are going to reform the hydroxyl functional groups for those alcohols. With our ketones, the carbonyl is in between two R groups or alkyl groups. Same process is going to happen where a hydrogen will go to the carbon and the other hydrogen to the oxygen. We still need that catalyst to break the hydrogen apart because it's not reactive otherwise. If we look at the process of reducing acetone or propanone with our hydrogen. We need that metal surface again that allows for the breaking of the hydrogen molecule into its separate atoms. Those hydrogens are now reactive enough to interact with the double bond of that carbonyl, breaking open that carbonyl double bond, allowing a hydrogen to be put back onto that carbon and a hydrogen to be put back onto the oxygen, reforming the alcohol. Because it is the second carbon in this compound that the OH group is on, that is what makes it a secondary alcohol. Therefore, acetone is going to reform into 2-propanol.